Welcome to the AWS Summit. In this session, we'll be covering the convergence of machine learning and high-performance computing. My name is Angel Pizarro. I'm a principal developer advocate for HPC at AWS. In this session, we'll cover a little bit of background about how Amazon thinks about developing services and products, and specifically, what is the flywheel that we use for these initiatives. We'll take a little bit of a deep dive into the AWS capabilities for HPC and as they relate to machine learning. And finally, we'll see how these two threads for AWS businesses, services, and customers tie together at the end. So first up, what is this flywheel? Back in the beginning of Amazon, Jeff Bezos wrote on a napkin this diagram about how we think about our businesses and how we think about developing better customer experiences. And it all starts with a good selection of products that drives a customer experience. In other words, customers come to Amazon and AWS for the selection of things that they can acquire. That good customer experience, as we reduce the friction for them to either consume a service or buy a product, drives more traffic to our platforms. More customers, more traffic, in turn drive more selection, more sellers, and it enters this virtuous cycle that drives the growth of Amazon across all of our businesses. In turn, that growth flywheel drives innovation. It allows us to lower a cost structure of something, and for the most part in the retail space, that means lower prices and better selection, which in turn go into much better customer experiences. So these flywheels are essential to all of Amazon and AWS businesses, but how does that really apply to HPC? How does that apply to machine learning specifically? Well, I took a bit of a swag at redefining that flywheel diagram in the context of HPC and machine learning. And you can see that we start out with similar concepts, such as the accessibility to hardware resources. And that really is the equivalent of selection for retail customers, is that you're able to acquire hardware, computational, and storage resources to even ask or answer the questions you might ask, right? So research starts with a question, but that question might as well not be asked unless you have access to the hardware to answer the question. So those are the beginning of the flywheel. Once you start answering this question, you drive into better results in data. Better results in data itself gives you more use cases that you can apply a method that you've innovated on, and more use cases and more methods that you get from that research and answering those research questions, again, lead to new questions about the problems you are facing. And having those new questions will again drive you to go where there is more accessible hardware, and thus closing the flywheel of virtuous growth for Amazon's machine learning efforts, for our services for machine learning and HPC, and generalized cloud computing. The growth, so what do we do for lowering our cost structure, is essentially when we're scaling, we make more hardware investments, not just in growing a region in terms of the amount of storage and computational resources that are available to customers, but also different types of hardware, evolutions of hardware, and process changes that allow us to do hardware choice, hardware innovation for our customers. And that in itself drives the accessibility, again, to be able to answer more research questions, more machine learning questions, as well as HPC, address further HPC problems that weren't possible before we made those hardware investments. And you can see this again and again across Amazon. For 20 years, the company at large has been leveraging machine learning and artificial intelligence to drive the customer experience. It's really easy to see it at the retail end when you go and shop at Amazon.com for a selection of products. But you could also see it in the operations. You know, the Amazon warehouses themselves use machine learning to do predictive analysis of what products should be procured in time for people to have that selection at their fingertips. It also drives innovation. For instance, the Alexa set of devices and natural language processing models were ahead of its time and really created a device category that wasn't there before. And we take that success and that innovation on behalf of our customers and apply it to new businesses all the time, AWS being one of them. So why is machine learning relevant to high-performance computing? It turns out that machine learning, AI, and HPC all share some commonalities, and specifically, they both solve complex computational problems in a distributed way, with trying to seek out the best performance from the underlying hardware so that they can get their answer faster. Some of the shared primitives are equivalent across the two domains, including things like the need for a certain type of CPU or architecture, memory bandwidth, network infrastructure, or other things at the software layer, such as schedulers for assigning work to and scheduling that work to be done in a complex workflow setting. The differences, though, lead into the question of why machine learning has been applied so much more than HPC across the different domains. And we saw a bit of an answer to that in the previous slides, in that machine learning has been applied to a lot more business problems than HPC has. Traditionally, HPC is categorized as solving tough problems from the perspective of computational needs that span tighter coupled set of resources in specific domains, right? So there's a lot of specialized software that goes into HPC to solve particularly tough challenges that were ahead of their time that could not be addressed by other sorts of computational infrastructure. So if we have that background of HPC needing some specialized, and really the sports car analogy of versus a minivan, of a HPC needing really performant hardware versus the minivan that's hardware that's accessible to a lot of different problems, how would you actually accomplish HPC on AWS? So let's go and take a look at what the picture is today with a little bit of background on how we got to where we are today with HPC on AWS. So today, we have virtually any type of HPC workload is possible on AWS. And we have customers doing all sorts of innovation and data analysis, whether that's weather forecasting, reservoir simulations in the energy industry, financial modeling, computational fluid dynamics, and computer-aided design, as well as medical imaging. And the huge difference between all of these areas and how you do it on a traditional HPC cluster versus how you do it on the cloud, it boils down to this, in that for traditional clusters that were delivered on premises, you had a high watermark for what you would be able to do, and then you had to schedule the units of work within that envelope of hardware that you had available to you. With the cloud, we shift that model on its head and say, what is it that you need to do right now? The hardware will be accessible to you, answer your question quicker, and scale the hardware resources need to the point in time questions that you're answering. And the driving force of why you would want to have a model like this, as opposed to a sort of long-lived infrastructure that is slowly changing, is this quote from Hyperion Research, where every dollar spent on HPC is bringing back really quite good returns on investment. In terms of incremental revenues, you see above $500, and in terms of profit, you see close to $50 per one. So when you have such a large return on investment for every dollar invested, it makes sense to want to answer more questions as you come across them, as opposed to waiting on the queue to answer that question and delaying or even skipping over the amount that you can invest and ultimately forfeiting that return on investment. And we saw an example of this quite recently with the story of our times, the pandemic, and the development of the vaccines that were really innovative by Moderna and other biopharma companies based on mRNA technology. And what we saw, the capabilities of our customer, Moderna, was that they were able to improve the processes with machine learning, especially the quality control and the operations of creating these vaccines, down to unheard of levels of innovation to get a viable vaccine in just 42 days, which is pretty amazing when you think about it. So we've seen now why the model of cloud computing is good for HPC, basically that you want to answer the questions more quickly. We've seen that at least one use case where it was used effectively to change our futures for the better. Now let's take a slightly deeper dive on what specifically does it mean to do HPC on AWS. And I'd like to call your attention to this diagram, especially the part in the middle with the pink zones. And what we are seeing here is that HPC on AWS relies on a lot of the same software and stack layers that you would do for on-premises HPC. You know, the fact that you need shared file storage systems that service a cluster of computers, and that the cluster of computers rely on services like license management or application distribution to solve the problems at hand. And finally, at the very top of the stack, your researchers or your data analysts or your HPC infrastructure team needs visualization frameworks in order to view their results, right? So HPC on AWS starts out at that bottom layer with shared storage services that we'll get to, that can be fed either from devices coming in from the internet. Your corporate data center can shift data in, or shared data from your customers and partners that are already on the cloud. And then from there, you can build on top of it to address the challenges that you need. HPC services that are available for you at each of those standpoints are listed out here, starting with some of these key ones that have to do with hardware, and we're going to cover these in further slides. But generally, it starts out with the core and foundational component of Amazon Elastic Compute Cloud. These are the instances that service all AWS services and cloud computing at large. I'll talk a little bit about our networking product called Elastic Fabric Adapter and how that's enabled HPC workloads and what the difference is with and without Elastic Fabric Adapter. And then there are other services, including FSx for Lustre, that service the storage needs for HPC customers, specifically based on popular open source shared storage file system called Lustre. Finally, not covered in this session, but be aware that there are software and services that help you orchestrate and manage these other components to enable HPC workloads, whether they're tightly coupled, strong weak scaling, or loosely coupled scale-out analysis on top of AWS. So to go back to Amazon EC2, when we first started the cloud, everything was virtualized on top of the operating system. And as I mentioned before, HPC customers and HPC users really demand the utmost performance of any hardware that they implement their systems on top of. And the virtualization overhead was just too much for them when the cloud first started off in circa 2008. To address the overhead of virtualization, AWS developed a Nitro system. The Nitro system consists of three components. There's the Nitro cards, which are the backbone of our networking infrastructure. There's the Nitro security chip that provides a secure root, a hardware root of trust. And then there's the Nitro hypervisor, which offloads. It's a lightweight hypervisor that does the memory and CPU allocation for our instance within an instance family to give you the instance sizes, and it also provides bare metal-like performance for HPC workloads. Speaking of instances, just to take it back a step, we have more than 375 different instance types across to address different types of workloads. And this is another difference from traditional on-prem HPC clusters that tend to be homogeneous with respect to the hardware and the service that they offer. So with the cloud, you're able to bootstrap services that address a particular application's needs, whether that's high memory bandwidth servers, high I/O throughput applications, or CPU-intensive, low data passing applications. The choice and the accessibility of choice is really central to how the cloud looks at solving HPC problems and other machine learning problems as well. To take a look at a specific type of instance, we released a few years ago the C5N family. And the two key HPC-related features of C5N that makes them amenable to leveraging for HPC problems have to do with, one, the internal to the instance architecture that allows high memory bandwidth for scaling a process to be faster within a single instance. And then across instances, we introduced a networking stack and hardware that allows us 100 gigabit per second throughput of network throughput across instances for low latency and low jitter bandwidth. There are other instance types that include this networking infrastructure, but we'll just highlight C5N for now. The networking innovation that I had mentioned before, it's called Elastic Fabric Adapter. We've proven out that this hardware-software combination is amenable to traditional HPC problems, which were historically not well addressed by cloud computing, such as computational fluid dynamics, seismic modeling, weather forecasting. These applications had assumptions about how networking happened and the requirements of networking across different instances talking to each other, so different servers talking to each other. And early on, the cloud was just not able to work as well as on-prem needs. With the introduction of Nitro, that gives us bare metal-like performance on individual instances, and then with the introduction of EFA, that gives us high-speed, low-latency networking, we're now able to address these problems. So what was the innovation here that really brought forth the EFA, inclusive of the hardware? The second part of EFA outside of the hardware was a new networking protocol that we introduced called Scalable Reliable Datagrams. And basically, this worked off of the theory that you can send a packet out of order to be received by instances across multiple paths. And what the difference between SRD and traditional networking protocols that are delivered in order is that you can recover incredibly quickly in the face of errors, right? And no system is so perfect that it won't be affected by some networking error at some point. So this graceful error recovery is really highlighting the difference between traditional in-order packet delivery, in that if there is a failure in these traditional network protocols, all operations just stop until the recovery happens. With SRD, since the packet is going out of order and in multiple paths, there might be a blip on your network, but you can continue on processing and retrieve that packet much faster and continue on with your application's work item. This product and innovation turned out to perform extremely well. And we saw that this networking change, this change in how we look at network performance and data delivery, had a real-world effect. So here's a study by the U.S. Navy on forecasting, a forecasting model. The graph here shows that to the left and down is better performance, and I'll highlight two lines on here. First of all is the green line, which represents the current system that they were using. That was on-premise Cray system. And the red line represents a cluster that was a C5N instances. And you'll see that we performed quite well. In fact, we had better performance in their on-premise system, as well as better performance than some other systems, including previous AWS instances that did not have EFA, which is represented by the orange line in the graph, which is up and to the right. So EFA makes a huge difference in this very traditional HPC workload that has tight networking requirements. The Navy is not the only folks who have looked at weather modeling and forecasting. Is obviously one of the challenges faced by a lot of our HPC customers. The experiment was repeated and put into operations by our partner DTN, and in looking at other sorts of architecture changes, we see that this experiment of hardware choice can really have benefits across other HPC domains, such as computational fluid dynamics. And here I'm showing a bit of a result from our partner F1, where they used our ARM-based Graviton2 instances to increase the better price performance of their application by 40%. Right, so they took advantage of EFA 100 gigabits per second networking on the C5N, C6GN family. They took advantage of the lower cost of our Graviton2 instances, and they essentially derived a lot of value for it. So price and performance is one thing. How do we address the issue of so price, obviously, and performance? Really, let's tease out what is the effect of performance. So we have this blog post here. You can see the link on the bottom left. You can also search for weather prediction on Graviton2 from our blog channel, and you'll be able to see the full analysis of this price and performance of Graviton versus x86 architectures. And I'll point out two charts from that particular blog post. First is the top one, where top left diagram, where you see across the number of instances, the x86 instance, the C5N family, and the Graviton2 instances, C6GN family. When it has EFA across the number of instances, the performance is almost exactly the same. If you're looking at per core performance, the x86 Intel C5N based family actually does perform better. So if you want slightly faster results with a lower number of instances or a higher number of cores, Intel is still the architecture of choice. But if you look at the bottom graph, there's quite a bit of difference in terms of the price for any given core count between those two different instances. So given the fact that, across the number of instances, you get similar time to result and a much better cost savings, we think that a lot of our HPC customers should look at ARM-based instances as a way forward, right? Finally, I'll bring to you one last hardware innovation. Let's put it all together. We've seen that the Nitro chip has been fantastic in terms of getting bare metal-like performance. We've seen that EFA addresses the networking concerns to give us high bandwidth, low latency networks that are tunable for HPC workloads. Let's bring it back to machine learning. Right, and this is where EC2 Ultra clusters come in. So these are NVIDIA A100-based GPU clusters that are all enabled by this extremely fast, low latency network of EFA. You're able to put together not just a CPU-based cluster, but also GPU-based clusters, since the GPU direct networking, so the GPU is talking directly to each other over RDMA, is enabled by EFA as well. So you're able to put these massive clusters together to train incredibly large models very quickly. And that same network fabric that serves the compute instances also serves our storage. So you get an extremely high bandwidth access through FSx for Lustre to these P4D instance clusters. All right. So we see that everything that we've developed for HPC is also being able to be utilized in the machine learning space. So just a word from our customer Triad. They were able to reduce their costs by 40%. Actually, their time to result by 40% by adopting P4D instances. But not only that, they were able to leverage the networking improvements to scale their models to dozens of instances where they weren't able to do before. And that caused faster training times. Faster training times lowered their costs. Lowering their costs allowed them to inspect more problems, answer more questions, make more models so that they get better predictions at the end. And in their space, which is autonomous vehicle object detection and smart city and doing better autonomous vehicle driving algorithms, being able to have more accurate models translates into better safety for pedestrians, for drivers, for everyone. So this is a worthwhile cause, really fantastic use of HPC technology that was developed for the HPC space, applying back and giving to machine learning, right? To To take it a step further, now that we have this flywheel, we've introduced hardware innovations, we've introduced software services that allow our customers to address their business problems. How do we make further investments for hardware choice? At this point, I'll bring up Amazon EC2 Inferentia instances. So this is a custom developed chip. So once you have a trained model, you have very low cost, extremely fast inference of data coming in based on that model's pre-trained data. This is a case where we see that the needs of machine learning are so vast that you can segment and give hardware choices to specific problems within the subdomain. So you can train models using traditional GPUs and CPU combinations such as our Ultra clusters. And then once you have those trained models, shift to a lower cost infrastructure to actually apply the models to data that's happening in your operations. So we hope that this hardware innovation, hardware accessibility helps you solve your problems. If you're new to AWS, you might be having some questions that this is a lot of information, this is a lot to take in, and where do I start? That's where our AWS Training and Certificates program comes in. If you'll go to our website, you'll see a ton of content that we've developed that can be accessed at your own time. We also offer in-person training classes or online these days, and the AWS certification program to help you level up your skills on the cloud, your operations, so that you can get your work done. Stop focusing on infrastructure, start focusing on addressing real business problems and solving those challenges. Thank you for your time. I'll remind folks to please fill out the survey, whether you find it useful, so that we can refine our content and give you better information in the future. Thanks very much.